Right, let's now get started. Yeah, quick announcement here, which is very important for your upcoming assessment as well. Your assignment number 2 has been released, and looking ahead, you're going to have your programming test number 1 after the reading week. I'll make sure I give you guidance like a PDF, hopefully shortly after Wednesday's class, so you can definitely get started. Take the reading week to get prepared for your programming test 1. I'll speak more about it once the guide has been released. I'll try to do that maybe before Wednesday's class, so I can walk you through the important stuff. But I would like to point to you guys on your assignment number 2. Instruction. I want to just point to you, just in case you haven't really gone to that yet. It's a very critical assignment before you can think about the programming test 1. So if you go to the instruction PDF on the e-class, all right, so notice that we do have some new programming requirements for the linked list. The idea will be you want to build every method on the linked list from scratch. There'll be no use of the library method. Not array list, not hash table, no nothing, okay? And I would like to point to you over here. On page number 4 of your assignment instruction. Right, so we already discussed quite a good number of examples. Well, we talk about more today for singly linked list. But if you want to see more examples, I will refer you to some some past videos which I spoke about during the Q&A session last year. So how you can reverse a list, how you can remove some node from the list, and also how you can shift the node, shift the entire list to the right, possibly by a certain position. So I think that these are nice problems for you to maybe try out before you tackle the assignment 1 question. So these are extra stuff for you. If you find a need, I would highly encourage you to really try them. If you feel so comfortable about linked lists, that's okay. So that's why I say it's optional but recommended. But what's required as a study for you will be to really get used to the notion about generic parameter. So that will be the stuff I wouldn't really cover explicitly in class. So starting from later part of Wednesday, or maybe after the reading week, I will assume everybody knows how to manipulate the generic parameter. So if you try to follow through these videos over here, took about 1 hour in total. Go over them. I think that one really walk you through what you should know about the generic parameter. You will need that for your programming test 1, 2, and 3. Oh, sorry, 1 and 2, not 3. I really meant assignment number 2, 3, and 4. You also need generic parameter. Right, of course, if you got any trouble, let me know. Visit my office hour. I can explain to you the details. But I think what I included in this page, that should be enough for you to walk you through the details. And your assignment number 2 has been released. You definitely don't want to wait until too late. I will give you the solution in time. So you still got about a week before the programming test 1. You can study through the solution and then make sure you're ready. All right. Do you guys have any general question about assignment number 2? Yeah.
I know you mentioned like in the top that you were about stuff like string builder and stuff like that.
String builder, I don't think you really need it in the actual test. So I would say just don't use any library classes. If you think you really want to maybe concatenate 2 strings together, just use the plus operator. That'll be fine. All right. All right, guys, any question about assignment number 2? Anything that's not clear to you? You just have to get started and complete the studies and then do the problems.
Also, the one question I have is like when I downloaded the assignment to start it, the class was in the test package. Is this supposed to stay there or are we supposed to move it to the
model? Okay, so model package should always be empty when you're given the starter projects. So the idea will be anything I give to you should be in the test package. Anything you're supposed to develop on your own, they should go to the model package. Yeah, we'll just keep it clean. All right. All right, if no questions, let's now move on. And also one more thing, I just released your assignment number 1 solution before the class. You can go to the e-class and then it's a PDF there. You can definitely find a link to the source code, but I don't really recommend you only look at the source code directly. Of course, if you feel very comfortable about the programming part, that's okay. But if you really need some guidance about the solution, I also include links to the solution video. Walk them through and then learn about the recursion. It's so important for this course. All right, I'll give you both options. Right, once you see the solution PDF, you will know what I mean. Any issue, let me know. All right, let's now do a quick recap about where we were last time, and then we'll continue from there. Today, we just mainly just try to solve more problems on the singly linked list. All right, let's take a look. All right, this is where we started last time. Okay, we talk about absolute indexing versus relative positioning, right? About these two. Make sure you know them. And also we talk about in order to implement singly linked list, specifically we want to have just a chain of nodes storing string values. So as you study through the background study in assignment number 2, you will see how you can make the node and also singly linked list themselves generic. So that's the study you have to do for assignment number 2. Otherwise, you wouldn't even get your code to compile. But what we talked about was, for the singly linked list, what we started with was you have a single attribute called head. But later on, we're going to introduce 2 more attributes. So that's what we talk about as trading the space for time. All right? Anyway, so these are the 2 classes. You have to make sure you understand the methods and also attributes and also the visualization, right? That's to help you how you can design your own algorithm. And we talk about how you can construct a chain of nodes. You got 2 approaches for you, right? You can review both approaches. And once you got a chain of nodes, how you can set the head of some singly linked list accordingly, right? We'll talk about it as well. Very easy. You just call the setHead method. But you want to make sure you do that in the actual solution. If you forgot about it, you will fail the JUnit test. And then we spoke about some methods, especially talk about get the size, counting the number of nodes in the chain of nodes in the singly linked list. That one there is going to correspond to how many nodes are there in the chain. So that's why it's a linear time operation, big O of n. Not that efficient. And similarly, we talk about how we can find the tail, the last node in the list. That one there, without any explicit attributes being stored in the singly linked list, that will also take linear time. All right? So having these 2 observations, we said that we'll rather declare 2 additional attributes at the singly linked list class level, namely the size and also the tail, and so that they can make some operation easier. We'll see. All right? That's about what we spoke about last time. So from now on, let's assume the following. In the singly linked list class, we actually got 3 attributes. We got a head, we got a tail, and also we got a size. Right? We got these 3 attributes. So if you just want to go to the tail, you can just have an attribute access, which is a constant time operation, primitive operation, and also to get a size. And one thing that's a catch, you always have to remember. Okay, let me put it down here, just to remind you. So from now on, we assume the following. So we assume in the singly linked list class, we have the head, we have the tail, and also we have the size. So these are all attributes. The consequence is it takes big of 1 time to get access to them. And then you have the catch. What's the catch? The catch is for methods that might impact the head, the tail, or the size of a singly linked list. The body of the method should really update these attributes accordingly. The body of the methods should update. We'll see example today. These attributes accordingly. It's a very important consequence when we actually declare extra attributes. You want to make sure every method that might impact either one of them, you should really update them accordingly. All right, so important. So these are the 3 attributes over here. And also, you may have to update these attributes accordingly for any relevant methods. Typically, it's the mutators method that you have to watch out for the 3 attributes. We'll see. We'll see many examples today. All right, let's now take a look. So this slide is where we ended with over here. So we got these two additional attributes. And a very common question, now that we got head and tail, why don't we have another references, maybe called second node, third node, fourth node, and etc. You may do that, for fun, for your own application, but it's not worth the space because in general, you simply don't know how many nodes there are between the head and the tail. It can be arbitrarily large, so that's why we don't really bother, right? But if you really want to do it for your own application, you can do it. It's not going to help you asymptotically too much. Okay, that's the point. All right, let's now try to do some simple one just to begin with. So today is mainly about problem solving. Right? Think about the example we discussed in the class and also the ones I recommend you to really study for your assignment number 2 and the actual problems you solve in assignment number 2. So these are the 3 sets of examples you want to make sure you get ready for programming test 1. Right, so the problem is we want to insert a new string, let's call it E. So that's to be the name for the parameter, to the front of a list. All right, that's what we want to do. And from this point, I think sometimes you might find it very useful. Before you even start writing the code, it might be easier to see how to actually visualize the effects of the method before you write the code. That might help sometimes. So I'm going to show you what I mean. All right, so this will be some hints over here. It could be a little bit vague. So you want to make sure the new head is going to store the data E, and it's going to point to the old head. Not very clear, but let's see what I really mean here. All right. So guys, for now, don't worry too much about this one just yet. That's a solution, which is pretty simple. Okay? I'll just give you some very quick idea. Let's say if you have already some singly linked list. Okay? Singly linked list. You got the head, you got the tail, you got the size, right? So these are the 3 attributes. Let's say the head and the tail. The head is pointing to some node over here, and the tail is pointing to another node over here, right? And somehow they are linked together, like that. Right? I'm just sketching, right? What does it really mean? When you want to define this method over here, when you say, I want to store a new node storing string E, what does that really mean? That means the following. First of all, I need a new node. And then that new node over there is going to store, for the data part, just pointing to E. Okay? Now, what's going to happen is like this. I want to make sure the new head is not here anymore. Instead, it is going to point to wherever this new node is. That's part 1. Part 2, I want to make sure this used to be the old head. The old head is no longer the head. Instead, it should be the next node of the new head. So these are the 2 pointers you have to make sure you change properly. Conceptually, that's what's going to happen, right? So I will highly encourage you, maybe for your assignment problems, before you even write a code, draw some picture to see how things should be done visually. That might just help you write a code, right? Right? So that's the conceptual idea for addFirst. Let's now take a quick look on this solution over here that corresponds to exactly what I just mentioned. Of course, there might be some details that's missing. Let's take a look. I want to add first, and with the data element E. First of all, I create a new node, head, which is really like this one here. And that node there is going to store the E, and then the head is going to become, the head that used to be here is going to become the next of this new node. So we are doing 2 things at the same time. Let me say it again. This constructor over here is what we spoke about before. It's like approach number 1. All right, you can review it. When I create this new node over here, I'm saying that I'm going to set its next element to be wherever the head is currently. That's what I'm doing. And then afterwards, I'm just going to update the tail and the size accordingly. All right, let me write down these 2. The tail and the size. Remember, these 2 are the attributes. Attributes updated if necessary. Then let's dive a little bit deeper into it. we're saying that if the current size is actually equal to 0, what does that mean? That means we're having an empty list. In that case, adding a new first element is going to make that element, that new node, the tail at the same time. That's something I'll trace together with you, right? That's a boundary case. And always, since you're adding some new node into the list, you should always increment the size unconditionally. So that's why the size over here is always going to be done without any condition here. You can see this implementation here for addFirst is pretty simple, only a few lines of code, but it says quite many things. Number one, you should know how to visualize the node is being created and set the references. Number two, you have to know how to update the tail and also the size accordingly. All right? Any questions so far before we start some tracing? Everybody's okay? Okay. Let's now do some tracing together. So what we'll do is let's trace line by line. This line here, and by the way, so you can also find this source code. Let me show to you. I already made the source code available to you, just in case you're not aware of that. If you go to the lecture site here, and then you go here, just underneath the slides, you can see source code, singly linked list of strings. So you can find all the source code I talk about in the class, right? Sometimes I believe some exercise solutions are also in the source code. So I'll leave them to you to really play with the source code. All right? So now you know how to find them. All right, let's go back here. Okay. This first line over here is going to create an empty singly linked list. Let's see how we can do that. So basically, we have the list over here. That one there is pointing to an object over here, singly linked list. Okay, SLL, which has head, tail, and also size. 3 attributes, right? And in the beginning, the size should be 0. No nodes has been pointed to just yet. Also, the head and the tail, both of them, they are references. They should just be null. So this is a very important diagram, actually, to show to you this is how we begin with for every singly linked list. So this is like an empty singly linked list for this one here, right? You can see the size attribute is 0. Both the head and tail, they are not pointing to any nodes just yet, right? Okay, so far? All right. And you can see there's some assertion here just to make sure. Get a size, get a first. All right. Get a first, by the way, it's just to get a head. Right? You will see that implementation in the source code. Okay. And both of them over here, get a size, we're now going to just return this value. Right? It's trading the space for time. So it's big of 1. And also to really get a first, it's like getting a head. That's also returning the attribute value. So both of them will just be big of 1. Right, just an aside. Okay, and let's now take a look to see how we can execute these 3 lines of code. That's the main job for us to do right now. Let's do it, okay? It's not too bad, all right? The first one, list.addFirst. So that means we're going to execute addFirst over here. And the list is the context object over here. addFirst, we want to add Tom. All right? What's going to happen is you're going to create a new node, first of all. Okay, let me create this node. And let me just put it here. Okay, I'm going to have a node objects. Okay, the node objects. And then the new node is going to store the E. What's E? Tom. Remember, every node has the data, has the elements and also the next, right? Elements and also the next. The element here is going to be Tom. And what about the next? It's going to be the current head. What's the head? Currently, the head is just null. Agree? So, just null. Okay, so far? And then, we're going to see whether or not we should really fix the tail at the same time. Oh, sorry, there's one thing I forgot. All right. Notice one thing here. This line here, what we just executed was by creating this particular new node. At the same time, the reference of this new node should be set as the head of the list. right? I forgot to trace that part. Just don't forget, all right? This assignment should also be traced. So that means the head, rather than pointing to over here, is actually going to point to this node over here. That's the head. And then when I get to this part over here, is the size currently 0? Indeed, it is 0. So that means I should really set the tail to be the head at the same time. So that means the tail over here, rather than pointing to now, is going to point to wherever the head is pointing to. That's what we have. That's about the first addFirst ever. Before the addFirst, you can rewind the video. We only got head pointing to now and tail pointing to now. After adding this first node, both the head and the tail point to this node, which makes sense. You only got one single node in there. It's both the head and the tail at the same time. All right? Are we okay with this? Okay? Hopefully it still makes sense. Let's try to get to the little bit more general case. All right? The second one. All right? The second one there, first of all, we have to still go back to this line here to call addFirst the second time. So I'm just going to draw the node maybe here. Okay? This is another node over here. And then we got the elements, and also we got the next. And what should be the element? The element should be mark. So the element there should be mark. And the next should be the current head, right? What's the current head? The current head is actually pointing to that new node we created before. So now the next is just going to point to over here. All right? It looks pretty much like the approach number 1 we had last time about constructing a list, if you want some analogy. All right? It's pointing to over here. All right? So that's about, and what should we do for this assignment here? We also need to change the new head to be this new node. So the head, rather than pointing to there, is now going to point to over here. Right. What's happened? Just before I do a recap. After this, is it the case that size was 0? I forgot one thing. In the previous one, I should have updated size to be 1. Sorry about that. I should have. When I was creating this particular new node, I forgot to also execute this line. I should have done that. All right, just don't forget. Okay. And now for the second time, when I'm adding this addFirst, in this case, size currently is actually 1. So I'm not going to execute this anymore because size is no longer 0, the edge case. And then, but I'm still going to execute size plus plus. That one there is going to increment from 1 to 2. All right, let's do a recap. About the second call to the addFirst, what have we done? We have created this particular node. Its next has been set to what used to be the head over here. And then that new node has been set to the new head of the singly linked list. And also the size has been incremented. All right? This is the kind of tracing you will really need to get through. Right? You will need that when you design a more complicated algorithm. So guys, any part you find confusing or it's okay, right? Or too simple for you? I hope that's a letter, right? I hope. Okay, let's complete that. Just to be sure. The final one over here, we're going to add first for Alan. Okay? So what we should do is we create another node over here. And then there's another node which has the elements and also the next. And the element here is going to point to just Alan. Just creating the node. So I'm executing, again, this line over here, right? And this time is Alan. All right, so what will be the next for this particular third node? It should be where the current head is. The current head is the orange one, which is pointing to here, the mark node. So that means after creating this node, it is going to point to over here. Okay? And we check to see whether we are now in the edge case, where we should really update the tail. No, because size is currently just 2. 2 is not equal to 0, so we bypass this one here again. But we want to make sure we increment size unconditionally. So that'll be from 2 to 3. All right? And of course, in the previous assignment, at the same time, you also set that head, rather than here, is going to be over here. All right, and let me now highlight what's the ultimate setup. This will be our singly linked list, and its head is pointing to this node over here. That points to the next node over here. That one points to the next node over here. And that one points to now is the next node. That's the final outcome. Okay? Picture could have been drawn better, but you can try yourself on the paper. I encourage you. All right? So after that, we can do some nice assertion here. First of all, list.getSize should be returning the value for the attribute, which will be 3. And we can try to assert about the data elements. For example, we say list.getFirst.getElements. So list.getFirst is going to give you the head. That one there, the element is going to give you Alan. That's why it's the Alan here. All right, one more. What if you say list.getFirst.getNext.getElements? What's going to happen? List.getFirst is going to give you this node. And getNext is going to give you this node. What about its element? It is Mark. Exactly here. So once you have drawn the diagram, checking assertion shouldn't be too bad. Assuming that your diagram was correct, of course. All right. That's about addFirst. Any question? All right. What's the running time, guys? Constant, right? You can try 2 different ways. Either you look at the code structure here. You don't even need to understand the logic. As we said before your written test 1, no loop, so constant time. Or if you think about what's really being done for addFirst over here, we're basically just creating this node here, setting some reference to here, and setting some reference from there. Setting reference is about variable assignments. That's also constant. All right? So addFirst is not bad for singly linked list. But if you want to add first into an array, you may have to shift all the elements from the first to the right. Right? Pretty much like what we did the other day, earlier. So finally, it's going to be big O of 1. Only about setting the head, tail, and also next references. That's the insight. All right, that's the running time. It's so basic. So in the written test number 2 or in the exam, you're just supposed to know what the running time is. I don't think you might be asked to really implement this, but I would say just understand what's really going on here. Yes, question? Oh yeah, of course. So here what I'm talking about is just a single call to the addFirst. But if you talk about this particular program, you're building up some linked list of size n. In that case, the program itself would be big O of n. Yes, that's a good question. Yes. All right, if no question, why don't we do just one more, and then we can take a short break. Why don't we do one more? Okay. All right, that's about the addFirst. And you can see some diagram here. Okay. And some exercise for you. Okay. So this one here, you can look into these 2 tests and then just try to see how these 2 tests are done differently. All right, you're going to look into the detail for the test, and then I'll let you do the exercise. All right. And we're going to take a look at how we can implement these 2. What I will do is I'll try to sketch some idea together with you on the paper. And you guys will have to implement this as exercises. Right? We wouldn't talk about its detailed Java code in class. Right? That's something too simple that you should really try yourself as well. Right? So for these 2, let me take a look. Why don't we try removeFirst? Right? What does it do? All right, removeFirst. And what I can do is I can just copy some list from before, and we can go from there. Give me a moment. Okay, just to give you some idea. Okay, let's say this is the singly linked list we have. Oh, too much. Okay, the first one. How do we remove first? So we have a method in the SLL class. So let's say remove first. All right. Yeah, you can see that's the header of the method. No parameter, just remove the first node. And what do we really want to do here? Diagrammatically, we want to remove just this first node, if any. And then after that, what should we set, potentially? Well, apparently we have to set the head, right? So the head, for example, is going to be over here. What about the tail? Do we also have to change the tail? Is there any scenario you can think of that we may have to change the tail? One scenario. Tell me the scenario, please. What element? Yes, exactly. Okay. So guys, I'm going to write down some notes for you. Okay. So basically, you have to, let's say for this particular example, right? You basically have to make sure this reference over here should be removed. And also the head should be pointing to this one instead. All right? And then, of course, you have to go down the pointer by 1 to 2. And also what used to be the head, it should not be pointing to here anymore. Okay? So there are 3 things you have to do. All right? 4 things. Number 1, number 2, number 3, and also number 4. All right? So these are the 4 things you have to do. Let me repeat. Of course, you got to decrement the counter since you're removing the first. And also, you have to make sure the new head is not pointing to here anymore because that one will be removed. It should be pointing to the next of the head. And then you have to make sure this old head, since it has been removed, what we want it to be done is to be garbage collected by Java. So you want to make sure you also remove this reference here and set it to null. That's what you got to do. Yes, question?
Well, yeah, once we set that reference to null, the JVM will just start.
Yeah. So what will be the exact timing to remove it? We don't care. Just make sure you do that. Just like a garbage collection. Yes. Okay. Good. All right. So you got to do 1, 2, 3, 4. First of all. Okay. And also, I'll give you some reminder about special cases. If the current size is simply equal to 1, that means after removing the first, the list would become empty. Right? That means after removal, the list will become empty. In that case, you also need to set the tail to be null. That would be some special case you want to handle. All right? Another special case. What if the current size is actually equal to 0? In that case, it's already empty. Can you remove the first node from the empty list? No, you cannot. So this will be some error, like exception. Nothing happened, but something will happen maybe to the caller side. Let's say if you try to do it, typically you have to give them some exception to say you're not supposed to remove something from the empty list. Yeah. Throw some exception. All right. So that's about remove first. Some sketch for you. Right? I think that's enough for you to actually complete the exercise. All right, the next one. What about addLast? All right, this one here. Okay, I'm going to write it down here. Let's say we got void addLast. And then here we got some string. And then we have some element E. I would say the addLast is kind of similar to addFirst, similar. But now, rather than adding to the beginning, you're adding to the end over here. So all the special cases that you used to consider for addFirst, you got to consider in a symmetric way for addLast. Let's sketch the idea. So let's say if I want to call, let's say list dot addLast. Let's say Jin. Right? So what's going to happen? I definitely have to create this new node for Jin. And the Jin since it's going to be added to the last of the chain, so it's going to become a new tail rather than new head. So we got elements, also we got next. So element here would be, let's say, Jim. And the next will be just null. So what we should do is, the last, what used to be the last node is going to become the second last node. Rather than pointing to null, it's actually going to point to this particular node. So this will be number 1 you have to do. And number 2, the tail, rather than the second last node it has become, is now going to point to this new node over here. Right? This will be number 2 you have to do. Are we good? Kind of makes sense, right? Yes, question? Yes, absolutely, thank you. And of course, you got to increment the size possibly from 2 back to 3, right? Absolutely. Okay, so you got to do 1, 2, and also 3, right? I may have missed some little details, but you can definitely fill out the gap. I'm just talking about the principle. Let me talk about one more thing, and then I'll take a question. What will be the cases that you have to handle as edge cases? Go ahead. Yes. Yeah, I agree. Yeah, that's nice. You can, or if you want to really write some code explicitly, you can also do that. I'll just write that. You'll be the same, yes. Yeah, you don't need to. Yeah, usually having some code duplicate is not really a good idea. So if you can call other method as helper method, why not? If the size currently is simply equal to 1, in that case, you can definitely, oh, actually, sorry. If size is equal to 0, beg your pardon. If size is equal to 0, and then you can either write a code or you can just add first. It will be the same. Because after adding the first, that node is going to become the head and tail at the same time anyway. All right? That'll be it. Special case. All right? Definitely try these 2 exercises. You can use the starter project I gave to you as a source code and try these 2. And write some JUnit test cases yourself. They should be quite straightforward to complete. If you got trouble even at these 2 methods, you got to let me know or let the TA know. Question? I would say it will be the same because addFirst itself is also constant time. So calling a method that's constant time versus writing some code yourself that's also constant time, asymptotically will be the same. So I would say here, whether you want to call the method or just write some code, I'll leave the choice to you. Doesn't matter which one you choose.
All you have to do is reset the head, right?
Yeah, exactly. You got to reset the head for sure. Alrighty. So guys, why don't we take a quick break and take attendance, and then we'll continue with more examples. All right, you can get your mobile device ready, please, and then I'm going to do it quick, so you can take a short break. Okay, I'm going to start the class, and then poll, and how about this one here? Okay, you can check in, please. You wouldn't. Yeah. All right, guys, we're taking attendance now. In case you're not aware, please do it now so you wouldn't miss it. Since to be stabilized, all right, so any issue? All right, if you've got any issue, please come forward. I got a sign-up sheet for you, as usual. Please come. Otherwise, I'm going to stop it. All right, take a 2-minute break and then come back. All right? We'll resume in 2 minutes. Trouble for you again? Okay, just bring your pen, and then we will have you sign up. Maybe use a pen from one of the boys. Hi.
That's a question about the reading test.
Come by my office hour. We'll talk about it.
Okay. When is it?
Check your syllabus. It's outlined over there. Okay, sounds good. Okay, go ahead. Trouble for you?
No, I have office appointment booked at 1 o'clock.
Oh, it was you.
Yeah,
Okay,
yeah.
sure.
Is it better for me to come in, or do you want me to do it over Zoom?
I think coming in would be
Come in?
better.
Okay,
yeah, since
yeah.
you want to have some maybe detailed chat, right?
Yeah,
so why don't we
for
do
sure,
that?
For sure. What I'll do is I'll go home because my assignment 2
Oh, okay.
is saved on there. I'll
Sure.
just grab a copy of it, put it onto my laptop.
No
and
problem.
we'll
1 p.m.
discuss,
1
yeah.
p.m. is good.
Yeah,
Yeah.
okay, 1 p.m.
1 p.m.
It's on 2043.
2043. In case you see the door is shut, just knock. That's okay.
Okay, okay.
Yeah. In case nobody answers, just wait a bit. Maybe I'm just out for briefly.
Okay.
Okay. I'll see you then.
Yeah, thank you.
Okay.
I just had a question about.
Yes.
So,
Yes.
I noticed that we're doing
Singly linked list.
Singly linked list. Sorry.
Yes.
And on the assignment, we actually never used any of those, any of that class because we only had the node class.
Oh, yeah, that's true. So that means you don't need to worry about things like updating the size attributes with a head.
Yeah, because I was curious as to why we weren't doing that because I wanted to make sure there was no
Yeah.
real. Because when we were doing this in class, but then I noticed the differences. I was like, okay, wait.
Yeah, that's good. That's good.
As well, it's fine that we implement our own methods that are similar to that, to be able to get the end of the chain, we can do all of that, right? Okay, perfect. I just want to make sure just in case there was
Absolutely.
we weren't allowed to do it for some reason because it's part of a different class.
No, it's okay. I think for assignment and the programming test, they will have just identical format. You only have to deal with the node class. I think it's because usually for the interview side, they don't really have that singly linked list class on top. They only got a node class. That's why I kind of adopt that convention.
Okay, I was
So
just
you can
curious
get-
because it was
yeah.
the code different.
Absolutely.
Varied a very large amount between in class.
Yes,
to,
yes.
The assignments when I was working on it, I was like,
Absolutely.
because I needed to get the tail, and I was like, why is the
Absolutely.
So I was reading over the code, and I was like, this is not what I would need to do.
You know what? That's a very good. Let me. I better write this announcement to clarify. Let me do that.
Because I fully get what's happening in class with the code, but I just thought it was
Yes, absolutely.
different.
I would say just maybe get used to these two different styles. Either,
Yeah, I think I've mostly gotten used to it. And just as a question for the removing a node, it's the order is you need to do it in that order, or is it?
I think the order, sometimes you may be able to swap maybe some assignments, but sometimes it may not be. So you got to watch out for what you do.
I was working on the second problem, and I've solved the solving part. I just need to remove the element that's the lowest.
Okay, sure.
Yeah, so I was just trying to figure out how to do that exactly, and then today going over it was very helpful.
Okay, awesome.
I was very close. I was just missing one.
Good man, no problem. But thank you for bringing that up to me. I'll clarify by writing. Yeah, thank you.
Professor,
Yes.
you haven't updated my attendance on Twitter.
Oh yeah, don't worry. Well, I may not actually get to it until very close to the end, so don't worry.
okay.
You'll be done.
So as long as I have.
Don't worry. If you sign up, you don't need to worry. All right, guys. We'll start in just one moment, please. All right, let's get started, please. Okay, we got about roughly 36 minutes-ish, and let's see how much we can do. If we cannot, we'll do it on Wednesday. Okay, so here's a very quick question for you guys, important question. If you want to review singly linked list later, especially when we cover also doubly linked list, maybe either later Wednesday or maybe after the reading week, always ask yourself, let's say, can you imagine, we talk about adding to the last. What about removing the last? Do you think removing the last can be very efficiently done using the tail? What do I mean? Let's say here, I want to remove this node. Let's say. Now, knowing that this node here is the tail, does that really help me to really get a removal done? That's something you want to think about, all right? For those of you who don't think that's the case, keep your thought, okay? I wouldn't expect some detailed response for now. Think about it, all right? It turns out removeLast is not as easy as you might think. We'll get there a little bit later, okay? Just remember, when we actually got this question here for you on the slide, that means we're going to talk about it a little bit later in the lecture. Okay, let's talk about this one here. Now, we want to do something that's inherently, naturally, inefficient for the linked list because it's relative positioning. So let's say we want to get to the middle of the list of certain index. If you want to say, I want to go to index I in an array, it's a primitive operation, constant time, no question about it. But for the linked list, if I say I want to go to a position I in the list, it's not cheap. It's going to be a linear time algorithm, I can tell you right at the front. But let's see how this can be done. Okay? And some hints over here. We are using the same convention about how large or how small the indices should be. So it should be larger than or equal to 0, and should be strictly less than the size of the array, like a length of the array, similar. All right? So the same convention, so there'll be no confusion. All right? And also, we're going to program the method in the singly linked list class. So that means you may have to update the head, tail, or size if needed. But as I hinted to you before, usually, if your method is supposed to only get some information like an accessor, you don't have to touch any of the attributes. But if your method is supposed to update maybe the structure of the chain, in that case, you may have to update these attributes. So that'll be the principle you can note down. All right? All right, let's now take a look. And this method here is incredibly similar to finding the tail. Incredibly similar. So I'm still going to do the tracing together with you. It wouldn't take that long, but I think it's worth the time for us to do it together. Okay, so now let's say we want to, let me look at the code structure first. Okay, get node add, and some index I. All right, and let me remind you, this method here should be in the singly linked list class, in the SLL class. Okay. It's an accessor. It takes I, return a new node, a reference. Okay, pretty much like a find tail, similar. And we have some if condition here to say if the I here is either too small or too large, then you have to give some error, kind of. And that one there could be, the best way to do it might be just to throw some exception. And throwing some exception object will be constant time. All right, so that will be the branch where it takes constant time to complete for signaling the error. And this part over here is assuming that the index is actually valid. Okay, I can write it down for you. Think about this part here is the case where the index I is actually valid. So this is where I is actually valid. Okay. What we do is we initialize some variable index over here to keep track of how many nodes we have already covered in the process. And we still got this current reference. By the way, you don't really need to call it current. I think current is a name that's very commonly used, so I just use it. But the current is going to keep track of which node we're currently looking at. Initially, the head. And we're going to keep updating the current to be its next. We saw this already a few times, right? And every time you want to update, you want to make sure you also update the index. The idea will be once the index value has reached to the I that we are looking for, that means we are done. And we can just return the current node, which should be pointing to what we are looking for. And a very important insight for you to know as well. I want you to take a look at this condition here, the while loop condition. We are saying that as long as index is less than I, we're going to stay in the loop. So when will we exit from the loop? We'll exit as soon as index is the opposite way, larger than or equal to I, right? Specifically equal to. That's very important insight for you to note. You will exit when the index is larger than or equal to I. Mathematically, it's going to be larger than or equal to. Practically, as soon as it reaches to equal, then we're going to exit from the loop. All right? So what we should do now is to really trace the code to really convince you that actually it works. Okay? Let's take a look. And what we want to trace is list.get node add 2. And we're assuming this particular list, which we constructed earlier. Okay? And of course, they should be tail and also size. I just didn't really update my diagram. But you can, in this particular example, we don't have to worry about updating the tail and also the size. All right, let's try to trace the code together. Okay? Line by line. First of all, we have index over here, and also the current. The current is just going to be pointing to the head. So head is currently pointing to over here. So initially current should also be pointing to over here. And we initialize the index to be 0. So current should be pointing to the Allen node. Index should be 0. And we check to see whether or not we should go into the while loop. So index, which is 0, 0 less than what's I? Notice that here we got the argument 2 over here. So that's why I here is 2. All right, that's for our example. So if you got 0 less than I, true, right? That means we have to get into the loop. 0 less than 2. So that's actually true, all right? So what we should do is we should really go into this particular loop over here. So that will be the first iteration. And what will be the first iteration do? It's going to update the value for index by ++. And then it's also going to change the current into the next. Let's try to document this, okay? So it's going to be the iteration number 1, okay? That one there is going to update the index from 0 to 1. And the current node is actually going to change into, current node used to be here before the loop, right? Now it's actually going to point to wherever its next is pointing to, which will be this one, right? So that one there is going to be current rather than pointing to here. It's now, it's now going to point to this next node over here. That's current. Are we okay so far? That's after the first iteration. So after the first iteration, the current will be the mark node. And the index will be just 1. And we got to check this condition again to see whether we should go to the second iteration. And index is currently just 1, right? It's already updated to 1. So 1 less than still 2, because the argument here doesn't really change. So this less than should be also true. That means we should still go back to the go to the loop for the second one, second iteration. All right, for the second iteration, we're going to update again index and also update the current. Let's do that. So index is going to go from 1 to 2. And for the current, it's going to be set to the next of the current, which is the Tom node. Right, you can see the way the current will move, right? So it's going to point to the Tom node. That's after 2 iterations of coding, of execution. So the current right now will be just Tom. And then, what about the index? The index will be just 2, as you can see from here, right? What about checking this condition again? That will be false. That means we don't really have to go into the loop anymore. That's it. And what do we return? We just return the current. The current is simply just the Tom node over here. So this is the node at index 2. That's what we have. Okay, are we okay with this? Not too bad, right? It's fundamental, but hopefully you're following the tracing. And what's the running time for this? N, right? Obviously, it's pretty similar to the find tail. What I will write down for you guys is to consider running time. Think about the worst is when the I here will require you all the way to the end of the list. So you need this many of the next references that correspond to the size of the chain, right? It's when I is equal to the list size minus 1. All right, that's the last index basically. All right, so big O of n. You can see at this point, when we are doing big O analysis, it's pretty quick because it's assuming that you already got some expertise on doing that, right? That's before written test 1. All right, any question about this? Get in the middle. I here could be 0, in which case we just get the first element. It could be 1, in which case we got a second element. The worst case is simply denoting the last elements, the last node in the chain, which will take linear time, worst case. Okay, okay, after this, let's now try to go further for maybe another example. That's true. That's true. Well, maybe the worst case will be when but I know what you mean. Yes, indeed. All right, that's what we just talked about. On the other hand, if you try to get to some arbitrary index into the array, that will be constant time. It's a reminder. All right, this one is more fun. Okay, guys, this one here. This one turns out to be conceptually, well, actually, implementation-wise, it's not too bad. Only a few lines of code you have to write. Let's see what we want to do. What we want to do is we want to insert some elements into index I into the list. So apparently this one here is going to update the size and potentially the head and tail as well. All right? How do we do that? Huh? Take a guess first. Yes, indeed.
Off the top of my head, you would just take the index I, previous index, well, the second index exists to begin with. See what the previous index is. Take replace the tail with the new index, and then change the head of the other index and fit it there.
I would say yes. So two things over here. Number one, when you talk about the concept of like I minus 1, since we want to insert into I, but somehow you have to worry about where is I minus 1 index. That's a good sign, number one. Number two, I would say only worry about head and tail updates as boundary cases. We'll do that maybe later. Okay, yes, go ahead.
So you use the get I from the previous slide to get the I minus 1.
Yeah.
Update that.
Yes.
The dot next to
Indeed. Indeed, absolutely. But guys, I want to give you guys the most important insight into this method here. Let's talk about it first, okay? Let's say this is a general case. Let's not worry about boundary cases just yet. When you try to program for algorithm, I would say don't bother with boundary cases just yet. You always start with the general case and worry about boundary cases later. That'll be a better process to follow. All right, so let's say we want to say add index I and then some element E, okay? Let's say we got an arbitrarily long chain of nodes. This is index I, okay? Here's one question for you to think about first. If I simply try to use the previous method I programmed, which will get node add, okay? Let me write it down. If I say get node add I, that one there is going to give me this, right? A reference to this node at index I. On the other hand, if I say get node add I minus 1, that one there is going to give me a reference to this node, obviously, right? So now the question is, would it be enough if I only make a call to index I and return to me this node in order for me to insert a node at index I? That's the question, right? If I actually want to insert, let's say before that, what's going to happen visually? Since I'm going to create a new node storing element E, let's do that first. So here, let's say we create a new node over here. Okay, this will be the node. We got elements. Yep. We got elements, and also we got the next over here. Okay, if you don't mind, I'm going to switch the position a little bit. Okay, I think this will be better. So the element pointing to this object over here, string objects. And the next, how do we set it up? What's going to happen is like this. After the method has completed, what we want to have is this node here should become index I. What used to be I should become I plus 1, what used to be, right? That's what we want to happen. So that means this reference here should go away. And we should really get this one here pointing to here, and this one here pointing to here. Let me highlight them. First of all, you want to get rid of this. Also, you want to make this happen here. Also, you want to make this one happen. Oh, sorry. You want to make this one happen as well. Visually, that's what should really happen. So this will make sure the new node you're inserting is after index I minus 1. So it's index I. What used to be index I is now I plus 1. Okay? Now, let's think backwards. In order to make 1, 2, and 3 happen, would it be useful just to make a call, get node at I? Would it be useful if I only got this? No, because if you only got reference to this node, how can you actually change this reference over here? Right? You can see we are thinking backwards to justify. Okay? So this update over here tells you need the reference to the node at index I minus 1. That's a visual justification. That's the insight you will really need very badly. All right? And it turns out getting this is not very useful. Useless for this case. All right? All right. That's a very important justification. If you got it, almost done. Question? Okay, good question here. Very good. Maybe I'm being a little bit too extreme, but I tell you why I would say that. Okay, you're right. In order to set this one to be over here, this reference is this. I agree. But calling this method will take another linear time, right? Every time you call that will be linear time. So why don't we just say, I set this one here to be the next of this. So that'll be cheaper in some way. Asymptotically, it will still be the same. But I would say in practice, maybe a little bit better. That's why. Yeah. Okay, but that's a good question. Yeah. How about this? I would say useless. Okay. Feel free to make another call to maybe index I. It wouldn't change the overall running time. It's just less efficient in practice. All right, let's now take a look. All right, so let's see what we should do. Number one, this test is also made available to you guys. So play with it. Run the debugger, see how things will work. Okay, I would say up to here, we are good. Up to here is about something just to use the addFirst to create this particular list structure. That's what we did before the break, right? And we can also now what we want to do is these two. Let's see how we can do it. So let's say the first one, add. Okay. Oh, let's look at the implementation itself, first of all, very quickly. All right, so here it's important to handle some error cases, right? We want to say if your current list is of size 0, it's empty, how can you remove? Oh, actually, let me see this. Am I insert? Oh, I beg your pardon. For some reason, I circled the wrong thing. Let me do it again. Add. Yeah, we are fine. Add, and then we got index, and also we got string over here. Okay, so what will be the error case? We are saying that if the I is either less than 0 or larger than size, in that case, you cannot really add. So now, what does that mean? So the I over here, it could be starting from 0 or up to the size of the list. All right? So this is the legal range of indices you can put. What does it really mean? When you say, I want to insert at index 0, that means addFirst. What does it really mean? When I say, I want to insert at index of value size, that means addLast. Agree? Okay? Something like that. All right, so here you would see we say if the I is equal to 0, that means addFirst. It's a helper method call. Right? That was straightforward. And then here, this is exactly what I just showed to you guys right before, right? In this page over here. Okay? What we need to do is we need to call get node at I minus 1. And then we're going to create some new node and set the references accordingly, and then increment the size. That's what we're going to do. Okay? Now, how do we do that? Yes, question? Yes.
If we get I that's the same size, it would be the same as
Yeah, exactly. That's correct. Yeah, exactly. So in the case where I has its maximum value, which is size, in that case, we're actually going to get over here, get node at size minus 1, which will be the last node in the list, in which case we're going to add after that. Right? Exactly right. Yes. All right, let's now trace the code together, shall we? The first case will be the simple one. Let's say we want to add first over here. First of all, let's create a node. Let's say I create over here a node over here. So this will be a node. And we got elements, we got next. Okay? And then if you try to execute this, and you can see if I is equal to 0. Indeed, I is equal to 0. That's a special case. In which case, we simply call the helper method add first, which we know how to achieve, right? So what's going to happen is we're going to get the element here, let's say Suyang over here. And add first is going to make sure the head is no longer going to point to here. It's actually going to point to this node over here. And also, its next is actually going to point to this node. That's the first one. Right? I'm assuming that we already know how the add first should work. And that's like a special case. All right? Let's now talk about the trickier case, which does need a little bit more attention. Okay? And let me just go a little bit further with you guys. So let's say here the size after adding the first node, right? I'm just put the size over here. Used to be 0, but it's now 1. Right? So sorry. Used to be 3, but it's now 4. Used to be 1, 2, 3, but now it's 4. Used to be 3, but it's now 4. And let's now try to trace this line over here. Okay? We want to add a new node storing UNA, let's say. It's going to count at index 2. Let's do some little bit of rehearsal. This will be index 0. This will be index 1. And we want UNA to count right after this. So it will be index 2. What used to be index 2 is now index 3, and etc. Right? That's what's going to happen. Let's try to trace it. And this one here, let's see here. And we definitely, this index 2 is actually valid. So we don't really throw any exception. And then also index 2 is also not equal to 0. So we also don't try to add first. That's not a special case. So what we want to do is these 4 lines of code that we have to execute one by one. All right? Number 1, the node before. We're going to get node at, and we also know how to do it. Right? You can see here, I is actually equal to 2 in our case. So we want to get node at, get node at 1. All right? What will be index 1? Index 0, index 1. That will be index 1. So this will be the return value from get node at 1. That will be node before. Are we okay with this? So that means the new node that we're going to create is going to count after this I minus 1 position, given that I is equal to 2. All right? And then the new node we're going to create. The new node is going to contain the string value, which is UNA, and then it's going to have this one here. So that's really back to the original question you had for me. Do we really need to say get node at I? We don't need to. All right? This is actually shown to you. Okay? Let's take a look. Let's create that node. Let me put a node here. So this will be the node. We got the elements, and also we got the next. Okay, let's be careful here. First of all, you can see the E here is just UNA. That one's easy. And what about the next? The next here is going to be node before dot get next. Node before dot get next is exactly over here. All right? So that one there is going to be next is going to point to over here. At the same time, oh, actually that's good. That's it. Let me try to give you some hints. So this is star. This is also the star. Okay. Finally, how do we set the final one? And no before dot set next. No before is actually here, that set next. Rather than pointing to over here, it's going to point to the new node. It's going to point to over here. And then we're going to increment the size from 4 to 5. I'm going to recap, but for now, what have we ended up with? We basically got, this is the head, and the next one here, and then the next one here, the next one here, and then the next one here. That's the new structure overall. Okay? Let's recap about the second case over here. We want to insert at index 2. Index 2 will be index 0, index 1, so index 2 should come right after index 1. So we should really get the no before at index 1. Right? So that's exactly what this line will do. After that, we're going to create this new node. And the next of this new node should be pointing to exactly this node here, dot next. We want to insert in between. Right? So that's why you got the get next over here. After that, we want to make sure this node before also set its next to be the new node. Right? That's the second set we have to do. After that, we increment the size. Okay. Guys, question? If you're kind of following, that's a good sign. It's not trivial to really see exactly what's going on, but what's really important here about setting references, reference aliasing, that's what linked list methods are all about. When you actually get to the more advanced method that you have to program, you just have to visualize what should be happening first in general, and then write a code accordingly, and then worry about edge cases. That'll be the usual workflow you should go through. It takes practice, right? Yes, question. You got a question? Yeah. Sorry, say it again. I don't quite catch you.
We apply both references like correctly.
Mm-hmm.
It's not in the list.
Yeah, exactly. Exactly. Yeah, yeah. You definitely have to complete the execution for the entire method before it's complete, right? Yes. All right. So that's about inserting something to the middle. Okay. Let's see what the next is. Okay. And do we have? Yeah, we have about maybe 7 minutes or so. We can do one more. Insert to the middle. Well, what about the running time? Guys, this is a typical example that we spoke about before, right? If you only look at the code itself, it has no loops explicitly. So should it be just constant time? Yes or no? Let me say it again. The solution here for add, it has no explicit loop. It got only if statements and some method call. Does that mean it will just be constant? It's hidden. That's exactly the two cases we spoke about when we first talked about primitive operation. This method call here, as we knew from before, takes big O of n. So that one is going to dominate. All right, so this one here already takes big O of n. And it doesn't really matter what the other steps over here might just be assignments and setting the references. Doesn't matter because that one's going to dominate. So overall, it's going to be big O of n because you're calling some method that's actually expensive. So no way around. All right, so that will be big O of n. Dominated by finding the node at index I minus 1. All right, so that will be the running time for insert to the middle. Not surprising, because if accessing to the middle takes linear time, of course, inserting to the middle should also take linear time. It cannot be just magically become constant time. All right, if no question, let's do one more very quickly. Right, you will see in the slide, also try to justify for you, right? How do I remove the last node in the list? All right, let's say this. Let me just try to be a little bit more focused, give you guys some idea here. Okay, let's say this is the list that we have. We know that we got reference to the head. Also, we got a reference to the tail. Let's say what we want to do now is we want to remove the last node over here. Would it be enough for us just to know the tail reference? Because, you know, potentially, since I want to get rid of this node, can I not just set this to be null? Isn't that already null? Or is that enough, or do we need something else in order to remove this last node? Somebody? All right, go ahead. Somehow, if you want to remove the last node over here, what you want to do is to really remove the next node over here by setting that to be null. But how can we get to this node? Do we have any explicit reference for that? We don't. We only got either head or tail. How can we get this one here? We have to get node at maybe the index minus something. That's what we have to set to get to this node. That one there, since we're calling get node at, is already make it expensive, but it's unavoidable. All right, let's now take a look. Okay, so that's why a very important hint is using the tail sufficient. It turns out it's not sufficient because you wouldn't be able to set the new tail accordingly. You wouldn't be able to. All right, let's now take a look. If you look at the code, if the size is simply equal to 0, in that case, you cannot remove anything. So there should be some exception. And if the size is simply equal to 1, that means currently there's only one node in the list. In that case, removing the last will be the same as removing the first. It's pretty much like adding the last will be the same as adding the first if the list is empty. Similar idea. And this will be the main thing that we have to do. All right? I only got about 2 minutes left, so I would suggest the following. Take a look at these lines of code. I would suggest you try to visualize what's really happening over here. It will be very similar to how we visualize the code, how the node creation and setting the references. Try that, and also try to trace the code over here. I'll try to spend about 10 minutes or so on Wednesday to finish this off, and then we can move on. All right, final reminder, so important for you to get assignment 2 started. If you really find this stuff challenging, reach for help. You don't want to panic too much during the reading week for your programming test 1. All right, thank you. I'll see you on Wednesday.